Okay, so today we'll start with a new topic. A, a little introduction of it was done in the last lecture, so I will just briefly recap what we did in the last lecture, just to make this lecture complete and so let me uh, give you a brief recap of what we did in the last. So we started out with the circuits which involves these kind of switches. If you see here, we have these switches, right? So we started off with this, and what we saw is, like, these switches can be either connecting the circuit to the source, like you have some source here, and these switches will either connect to this circuit or it will disconnect the circuit from the source. So there are only two possible ways of dealing with these type of switches, and normally the switching action takes place at t is equal to 0. We will see when the switching actions will take place at any arbitrary interval, that is at time t, or maybe at time, for any time t. Right now here we are discussing, for present we are discussing only for time t equal to 0. And we saw that last time, if we draw a time axis like this, and then if we take 0 is the point, because this is the point where this switching action is taking. So what we discussed was that we will have three different points close to 0, two different points close to 0, and the difference between these points with the original 0 is very less, like let us say 10 to the power minus 14, and it's not measurable also. This is basically done to simplify our analysis and thinking, so that's why we are incorporating a 0 plus and 0 minus type of concept along with 0. But all three of them are same actually. And then we have one limit which is minus infinity, and another one which is at plus infinity. So these are the situations. And last time we discussed that this particular area where we have from minus infinity to 0 minus, or you can say 0 also, you can include up to 0 or just before that, so that is 0 minus. So this area is called as steady state. Why it is called as steady state, can anyone tell me? Yes, like for example, at this point when the switch is open, whatever currents and voltages are there in this capacitor, they are settled down, they are not fluctuating anymore. So they are settled down and there is no fluctuation. That's why all the currents and the voltages in all the circuit branches will have a steady state value. And by steady state means, if you recall, what I am saying is, after these transients, when it reaches a fixed value, when you apply a DC voltage, this is basically called as steady state. This is steady state. If you recall our earlier lecture, I already discussed this. And then we have from 0 plus to infinity also we have steady state. And where is the transient? Specifically, yeah, in the last lecture I made a mistake. It will be from 0 to 0 plus, then we'll have a transient in this region. And why this transient is happening? This is happening because there will be change in the environment which this source is actually looking into. So if you see here right now, at time t is equal to 0 and before that, this source is looking at an infinite resistance, right? Because it's not connected to any circuit. So this circuit is not connected. So basically it's an open circuit like this. So this voltage source is actually seeing a infinite resistance like an open circuit here. But the moment you close this switch and you make it like, at time t is equal to 0 plus, at time t is equal to 0, you close this switch. So what happens is, between 0 to 0 plus, it will see some change in the environment, and the change in the environment is that earlier it was open circuit, but now it will see this resistance and capacitance connected to this voltage source. So suddenly from an open circuit, it will see a resistance and a capacitance. So there is a change in the environment. So that change in the environment will give you transients. And once that, yes, in 0 minus it will be steady state. So the thing is, once it sees this environment, the new environment, then it becomes comfortable with that. Earlier, as you can recall, for this open circuit also, this voltage source was comfortable, and that's why we had this steady state situation. But the moment this voltage source sees this resistance and capacitance, which is a new environment for it, it creates a transient. So there will be some trouble or some unrest in this voltage source, and that unrest is this transient. But later on, that it will get used to this type of resistance and capacitance. So that's why we have a steady state again once we move from 0 plus to infinity. So any questions here? Minus infinity to 0 minus, you can say, just to avoid the ambiguity at 0, because I don't want to bring in 0 here, so it will be up to 0 minus, and both of them are same. But what happens is we try to avoid this 0, because it's a step, and step is discontinuous. So this particular stepping is discontinuous, right? So we do not want to go into the details, like because this is a step, right? So at this point, if I want to know the value, what will you say, whether it's 0 or whether it's 1? So to avoid this ambiguity at the discontinuous point, we are having a concept called as 0 minus and 0 plus. Both of them are same, but still, okay? Is it okay? Yeah. If capacitor is not there, no. Then it will. One has to be there. One is either the capacitor or the inductor. Okay. Because resistances do not have any involvement with respect to time. If you see the relationship of V and the voltage and the current across the resistor, it is not dependent upon the time. Whereas case of capacitor and the inductor, they have this dependence between the voltage and current, and it depends upon the time. That's why transient comes mainly because of these two. Okay.
तो सर 0 प्लस को हम ट्रांसिएंट कहेंगे ना, स्टेडी स्टेट नहीं होगा ना 0 प्लस.
Can you repeat again?
0 प्लस पे ट्रांसिएंट ही होगा ना.
हाँ, 0 plus पे transient होगा. After that, somewhere after, maybe you can say 2 times 0 plus, from there to a long time, if it is gone, or to be precise, I will tell you what that is. After 5 time constants, we will tell you what this time constant is of the circuit. So after 5 time constants, things settles down. So the transients will actually goes completely towards 0 after 5 time constant, and then whatever value that you will get from after 5 time constant till infinity is steady state. Okay.
Sir.
Yes.
So the value which we get in steady state from minus infinity to 0 minus and 0 plus to infinity will be same?
No, it will not be same. It depends upon how this value, how this capacitor is seeing what kind of resistance and capacitance is. So for example, I will discuss this in the coming lectures. You will get to know this, but it's a good question. The thing is, if you have something here, right, along with this thing, right? So at time t is equal to 0 minus to minus infinity, maybe this capacitor will see some resistances, but once this switching happens, it happens to be like that some other circuit will form, and in that circuit this capacitor will see some other resistances. So at that time, the voltage division and the voltage that will come out on the capacitor will be different. So it can be different also, and it can be same, depends upon how the circuit is formed. Okay. It will not be the same. We will discuss the example once we finish off with this concept. You will get to know the answers to this. Okay. Any question? Any other doubts? Okay. So So what happens now is, with respect to all these breakpoints which I have listed out here, we have various, various terms like v0 minus, v0 plus, then we have yv minus infinity, then we have plus infinity, then we have I of 0 minus, I of 0 plus, I at minus infinity, and I at plus infinity. So what is this all about? This is basically the voltages and the currents which are actually flowing in the circuits at different time locations. So normally what happens is, a general current and voltage relationship, it will follow some differential equation. We will see that a differential equation is formed that relates the voltage and the current at any time t. But sometimes we are interested in knowing some specific points, like without solving this differential equation, can we get these answers like this one, this one, this one, and this one? These are all also called as boundary values. This is also called as boundary values. So normally why we require these type of points? We require these type of points because you will come to know this in a while. Normally when we solve differential equations, we have some constants coming up when we solve these differential equations. So that values of the constants can be determined only when we put these boundary values into that equation to get these constants. So I will discuss what I am talking about, but for now you can just think that these are the specific point of interest for us, and from these values we will able to calculate the constants which are appearing when we solve differential equations. So we will get to know what I am talking about. But if I write v0 plus or v0 minus or v minus infinity or v plus infinity, I hope there should be no doubt in what I am trying to ask you about. Like if I am asking you v0 minus, what you have to do, and if I am asking you v0 plus, what you have to do. Any questions here? Okay, so if there are no questions, let us discuss the capacitor. As you know, capacitor involves time in it. That is this dVt by dt. You can see here we have this time factor involved. So let us see how can we formulate this capacitor when it undergoes switching action. So let us say we have this time axis for the capacitor. Again I am drawing it here. So this is this. Okay, so now can you tell me, like if I am in this region, let us say after 5 tau, please keep this in mind that tau is a time constant. We will discuss what this is, but after some time, which is 5 times tau, we are reaching to the steady state. So can you tell me what will the capacitor be in this steady state? What will be the state of the capacitor? Sorry, can you tell me the reason why it will be replaced by an open circuit? Can you tell me the reason?
Because it was all the charge of the circuit basically in it.
So what?
Current is allowed to go to it.
So what?
No current is allowed.
No, but if it is storing the charge, then what's the problem?
That is voltage change is not allowed.
Voltage change is not allowed?
As much as it would become as.
No, that's not the reason.
So it is amount of charge leaving is equal to amount of charge that is coming.
So what can you say about the current in that case? Like if you are saying the amount of charge leaving is same as amount of charge arriving into the node, what can you say about the current which is flowing in that capacitor? Is it a constant current? Steady state current, right? So basically what happens is, basically what happens is, when I am saying steady state, it means it is stabilizing and the voltage variations are not there. So Vt is actually not varying at all. So there is no variation in the Vt, it is nearly constant. So all the voltages and the currents are stabilized because of the earlier fluctuation created due to the transients. Once the transients are gone, voltages are stabilized and it has a fixed value now. So as you can see now, if it's a fixed value, if you take the derivative of that, what will be the answer? Sorry?
Then IT will become
Yes. So IT will become 0. So if IT becomes 0 in some circuit, what can you say about the state of that circuit, whether it's a open circuit or a closed circuit?
open circuit.
Open circuit. In open circuit, there will be no current, right? So we already discussed it a lot. So in this state, it will be a open circuit, or OC, or you can say open circuit. And what can you say about this state here? In this minus infinity to 0 minus, what can you say about that?
Sir, again open circuit.
Good.
Open circuit. Open circuit.
It will be again open circuit because during this time period also currents are stabilized and there is no fluctuation. Fluctuation is happening only in this region. So here also it is stabilized. So it's open circuit here. Okay. Now I think what we can do is we can replace the capacitor, which is over here, with a open circuit like this if it is between minus infinity to 0 minus. So if it is between minus infinity to 0 minus, you can replace it by a open circuit here. And similarly, if it is between 0 plus, or you can say 5 time constants to infinity, again it will be a open circuit. Okay. Now the important part comes when it is switching the actions, like when your switch is closed. At that time, what will happen? So let me show that. So you know that we have already discussed that the voltages across the capacitor will remain same during the switching action. I have already discussed it in our very early lecture when we were discussing about the capacitors. That is, the voltage across the capacitor, if it is Vc, it will resist the change in the voltage. So if I am writing Vc in bracket 0 minus is equal to Vc at 0 plus, will that signifies what I am telling? Are you able to understand? If I write like this, is what I was telling in words? Is it correct?
Yes, sir.
So at switching, because at 0 switching is happening, so before that is 0 minus, so whatever the capacitor voltage was there at 0 minus, the same capacitor voltage will be there at 0 plus. This is we have already discussed, and this is the basic thing in the capacitor, because capacitor resists the change in the voltage, otherwise your current will become infinite or infinite. So this is the important thing that has to be kept in mind. The voltage has to be same. So once it is same, what can you say about let us say in the just a second, sorry. So let us say if your Vc at 0 minus is 0 volts, let us say, it might be the situation that your capacitor voltage at 0 minus when the switch was not closed, like for this example only, if you see this example here, switch is not closed. So initially we are not given any information. So the capacitor voltage is 0 or not here? It will be 0 or not if it is uncharged. So if it is 0, so Vc 0 minus is 0 volts. And then when you close the switch, then what will happen? Vc 0 plus will be equal to Vc 0 minus, which is the earlier voltage which we had. So now what will happen? It will also be 0 volts. Will it be or not?
Yes, sir.
So if it is 0 volts, then which kind of circuit is it? Where you have a where you have a 0 volt across it. What kind of circuit is it? Short circuit? Okay, so you can actually replace the capacitor by a short circuit like this if you are going from 0 to 0 plus, provided the VC 0 minus is 0 volts, then only you can replace it by a short circuit. But now let us say your VC 0 minus has a 5 volt, or you can say a V1 volt initial voltage on it. It might be the case that it is initially not uncharged, it is charged with the voltage of V1. So if you have something like this, then if you apply continuity equation again, then what you will get? You will get an answer as V1. होगा या नहीं होगा? Will it be or not?
Yes, sir.
So what is this? This is a voltage source.
Yes.
So if it is a voltage source, then it will be replaced by a battery of value V0. Depends. So now you have to be very careful in doing this. You can replace it by a short circuit if the voltage at 0 minus is 0 volt, then you can replace it by a short circuit. But if the capacitor has an initial voltage across it, then at 0 plus you have to replace it by a battery of voltage V0. Okay, any questions here? So this is very important thing which you have to keep in mind. Otherwise, it will be very difficult for you to go further in this particular topic. So you have to be very comfortable in understanding when it is open circuit, when it is short circuit. Okay. Okay. Can you repeat again what you are saying? Your voice is breaking. I cannot hear you. Please, just a minute. There are a lot of people actually speaking. I think it's better to raise your hands first than to speak all simultaneously at the same time. Okay, so 1022, you speak first.
Sir, can you please tell why this VC 0 minus equals to VC 0 plus, that I will understand?
This one I have already covered in our earlier lecture, so you have to go through there and recall from there, because I cannot repeat that here now. Okay, I have already covered it.
Okay.
So the important thing what I can tell you is, like, this basically creates a spike in the current, and currents become infinite. So we have to avoid that, and just to make that case, I have already discussed it. So you have to check back and see that. Okay. Any other question? Okay, so if there are no questions, then I will be going to the inductors. The second part is inductors here. So you know that current is L di by dt. So here, if I draw the time axis, this is 0, this is 0 plus, this is 0 minus, this is infinity, and this is minus infinity. So again, what will be the state of the inductor here? In the steady states, can anyone tell? Who will tell me this? Sorry, this will be voltage here. What will be the state of the inductor? Yes. Right. So you can see in the steady states the currents will be a constant value. So L di by dt will be 0, and that will give you a 0 here. So once it is 0 means the voltage is 0. Voltage is 0 only in the case of short circuits. So inductor will be replaced by a short circuit here. It will be a short circuit like this, and similarly here also it will be a short circuit. Okay. Now comes the transient part. In the transient part, if the inductor has no initial current flowing into it, then that in the if you apply the continuity equation of the inductor, you already know that IL at 0 plus is same as IL at 0 minus. You know this thing, right? So once this is there, IL at 0 plus is same as IL and 0 minus. What will happen, like if in case of IL 0 minus, initially if you have 0 amperes of current, then IL at 0 plus will also be having 0 amperes of current, because of the continuity equation that we have over here. So if I say IL 0 plus is 0 amperes, what kind of circuit is this?
Open circuit.
Open circuit. So it will be open circuit here. From the in the transient part, it will be a open circuit, or you can say this is up to 5 tau. So this boundary is actually 5 tau. So it is open circuit from 0 plus to, or can say 0 to 5 tau. And how about if you are having an initial current in the inductor? If you have an initial current in the inductor, at that time IL at 0 minus will be, let us say, I0, then IL at 0 plus will also be I0 or not? So it will be replaced by a current source of value I0. Fine. And note that these values like open circuit and this one will die down, because you can see after 5 tau seconds it will not remain a current source. It will die down and it will go to 0, and it will short after the while, right? So this is basically the thing, and you can see now how inductors are from short becoming either open or a current source, and then again becoming short. So this is the transient phase actually, which creates troubles. This is the transient phase which creates these type of oscillations. And once that is done, you can see this steady state is coming because of these behaviors which are short circuited here. And similarly, in case of capacitors, you can see how it is getting from open circuit either short or a voltage source, and then again becoming open circuit after a while. And you can remember that this voltage V0 is also temporary. It is up to 5 tau seconds only. After that, this voltage source will go away and you will get an open circuit. So if I want to tabulate the theory like what we have discussed, then we can draw like this. If you have a resistor, then this resistor will remain a resistor. If you have an inductor, then it will become an open circuit. This is at the time t is equal to 0. At time t equal to at time t equal to 0 minus, you can say. Okay, and this is the these are the elements, and they are this is the equivalent circuit. This is the equivalent circuit at time t equal to 0 minus infinity to 0 minus infinity to 0 minus. And if you have a capacitor, then it will be replaced by a short circuit. And if you have a inductor with the initial current I0 flowing in it, then it will be a I0. No, it will be it will not be this, it will be from 0 to 5 tau. And similarly, this one, if you have a capacitor and if it has a initial charge on it, then it will be replaced by a battery of value V0. This is V0. And at time t equal to infinity, if you want to look for the value of what resistor will look like, it will look like a resistor only, and the inductor will replace by a short circuit, and the capacitor is replaced by a open circuit. So these are the states. I have discussed it in here in a different format, but this is just the summary of how the elements will look like when they undergo transient analysis. Okay, any questions here? So you are okay with this now? So no confusion here, right? So if there are no questions, so let me move forward now. So let us try to solve some theory. Let us try to develop first the theory, and then we will solve questions based on that theory. So let us say you have a voltage source here, Vs, and then we have a resistance like this, and here you have again, these are the 2 points, and then you have again one resistor and a capacitor here. Okay, and this is basically the switch you have here, and this switch will indicated like this, and it will be shown that at time t is equal to 0, this switch earlier was at this position, and then at time t is equal to 0 it will be switched to this position at time t is equal to 0. But earlier it is connected to this point. Okay, and we have these resistance values as Rs and R, let us say. So at time t is equal to minus infinity to 0 minus, we are in steady state, right? We are in steady state. So what can you say about the capacitor at that time? What can you? Capacitor will be open circuit or not? From minus infinity to 0 minus. Will it be open circuit or not? Okay. So we can draw a circuit from minus infinity to 0 minus state will look like this. Right? Hoga? It will be from minus infinity to 0 minus, the circuit will look like this, and you can see the voltage across the capacitor at 0 minus will be equal to Vs. Will it be or not? So whatever voltage you have here, it will come out to be at the 0 minus, because there is no current flowing here, right? So current is 0. So whatever capacitor voltage at 0 minus will be the voltage Vs. Okay. So now once this is done, and we know from the continuity equation that Vc at 0 minus is same as Vc at 0 plus. So Vc at 0 plus will also be equal to Vs. Right or not? So you keep this in mind, that the voltage across the capacitor at 0 minus will be same as the voltage of the capacitor at 0 plus, and its value will be Vs. You keep this in mind. We will actually use it after solving something here. So now we will draw the circuit at time t is equal to 0. At time t equal to 0, what will be the circuit? Circuit will look like this. Will it look like this or not?
Yes, sir. Yes, capacity is charging.
Right? So it will look like this. So once the circuit is looking like this at time t is equal to 0 to, this is because your switch is now this side, right? You are connecting the resistance through this point, right? Now the switch is connecting to this point. So you have only R and C now, right? So here we have this. So now if I want to write the KVL here for this particular circuit, then it will be minus Vc minus Ic times R equal to 0, or you can say Vc plus ICR equal to 0, and then you can write the equation of the capacitor current with the voltage relation that we have. So what is that? It is RC dVct by dt equal to 0. All these are with time actually. So note that sometimes I miss it, but they are all function of time. So you can get this equation. Once you have this equation, you can readjust it like this. And then you have this as a differential equation. So once you have this differential equation, you can actually use, let us say, A equal to 1 by RC. This is just for the solving purpose. So once I use A is equal to 1 by RC, I can write the differential equation as A Vc t equal to 0. So now once we have this, we can actually solve it through various ways. So one of the ways is to replace this time t with another time variable t dash, which will not hurt the performance. So once we replace t by t prime, it will not change the things. It will still remain the same. The equation will still remain the same. And what we do is we multiply left and right by e exponential at half, at dash. So first step is to replace t by t dash. So if I do that, it will become like this. And then in the second step, I am multiplying left and right side by the exponential function. So if you do that, then it will become like this. And I think you must be knowing it, like if I can write like this or not, d by dt vct e to the power at prime equal to 0. Can I write like this?
Yes, sir.
Okay, so this is easy, right? So this is just the differentiation of these two terms, and if you expand it, you will get these terms. So there is no, rocket science here. So it's a very simple, differentiation that we are doing here. So chain rule we are applying here. So there is no, rocket science. So once you have this, what you can do, you can actually integrate between 0 to t, this particular differential which you have here. So once you do the integration of this particular thing, the derivative will go away and you are only left with the integrand, and that will be actually this. And then the limits are between 0 to t, and this is also equal to 0. So once you substitute the limits, what you get is this. And then once you write the equation by adjusting the terms, you will get this. And the important thing is, this is basically the constant that we were actually talking about. So this VC0, you already know that this is basically nothing but the one which we had calculated earlier. So let me show you that, this one. So this is these are the boundary conditions actually. That's why I was telling you earlier. Maybe I don't know whether you have studied it in your schools or not, but these are called as the boundary conditions, in which the values which are given over here will be substituted to get to the constants that we solve for the differential equation. So this value of Vs can be substituted here because it's Vs here. So you can write it as Vs e to the power minus at. So we have a general capacitor's voltage, as a function of time as this. So this is the thing, and you can replace a by what? 1 by RC, right? We have replaced. So this is the thing. And in electronics, what we call RC as the time constant. So this is basically tau. So you can replace it as y Vs e to the power minus t by tau also, BCT. And if you want to, and you know that this is basically for t greater than 0, right? So if it is greater than 0, this equation is valid for t greater than 0. So you can actually write in other way also, where you can write it as ut. You can multiply the unit step function with this, and you can remove this constraint here, which I am writing that t is greater than 0, because t greater than 0 is incorporated in unit step function. So this can also be another way of representing this waveform, but in this particular case you have to write the time index also along with it. Here there is no need of writing the time index because ut is actually taking care of this time index. So now if I want to plot the curve, then I think you must be aware of it. So once you have this is the voltage across the capacitor with time. So you can see that earlier, from minus infinity to 0 minus, its value will be Vs, and then it will, gradually goes down. And at time t is equal to tau, which is what we were telling here, t is equal tau is equal to RC, right? So at time t is equal to tau, the value of the capacitor reduces to 0.37 times the original value of Vs. So originally if you had Vs, then it will reduce to 37% of that. So basically at time t is equal to tau, it will reduce and it will go down to 37% value. And it has been shown that if you go to 2 tau, the value actually reduces to 14% of the original value which is here. And if you go to 5 tau, so let us say this is 5 tau, that's why I was telling you 5 tau. So if you go to 5 tau, then it will reduce to 1% of the initial value. So 1% of the initial value means 1% of Vs. So it will be here 1% of Vs. So you can see that all the transients which are happening here dies down after 5 tau seconds. So that's why I was telling you there when we were writing this, right? So from 0 plus to 5 tau, we assume that all the transients actually dies down. So that's why I wrote 5 tau, and from 5 tau to infinity you will have steady state values. Okay, so this 5 tau is coming from this particular analysis. So if I give you one question here, let us say you have this 20k resistance and then you have a switch like this, and then you have a capacitor of 5 microfarads, and the voltage across this 0 minus is 24 volts. So can you tell me what is the voltage VCT for any time t greater than 0? Can you tell me what will be the answer? So basically switching is happening like this. Sorry? What will be the answer?
24 into e raised to the power minus 20.
Right. So this is the answer. It's very easy, right? So you know that voltage across the capacitor at 0 plus will be 24, right? So that 24 will come out at this point, and then we have minus t by tau, and tau is nothing but RC. R is you know 20k and C is 5 microfarads. So you can multiply the two together, you will get this as the answer. So this is the capacitor voltage at any time t greater than 0. So let us try to form a general way of solving this. Earlier I have taken a liberty that we have only one voltage source. Let us take another way of solving it where you have another voltage source also like this here. So let us solve this particular case, which is a more general case as compared to the case which we have discussed. It's a very special case of that general case. So a more general case will look like this. Here you have Vs1, then you have this is the position 1, and this is again you have another voltage source which is Vs2. This is position 2, and then you have a resistance R, then you have a capacitor here C, and you have a switch which at time t is equal to 0 will move from 1 to 2. So when it is at 1, then you have time going from minus infinity to 0 minus. At this point, capacitor will be open circuit or not?
Yes, sir.
So it is similar to the
Yes, sir.
thing that we were doing earlier. So it will be open circuit. So it's open circuit, and in open circuit, the voltage across the capacitor at 0 minus is Vs1, and we know from the continuity equation that Vc0 minus will be same as Vc0 plus, and it will be Vs1. So this you keep in mind first. Now at time t is equal to, let us say, infinity. At time t is equal to infinity, what will be the case? Can anyone tell me? It will be open circuit. So you can check back at the back side of your slides. It will be a open circuit. So if it is an open circuit, then Vc at infinity is Vs2 होगा ना? Okay. So you keep these 2 points in mind, like Vc infinity as Vs2, Vc0 minus and Vc0 plus is Vs1. So these are the 2 points that you have to keep in mind. Now we will draw the circuit for t is equal to 0. So at t is equal to 0, if I draw the circuit, will it be or this or not? Vs2 R, then we have a capacitor. ये होगा? Will it be or not? So once at time t is equal to 0 you draw this circuit, then you write the KVL for this. It will be C dVc by dt or just a second. So Vs2 minus IR, and then what is the value here? What will we write here?
Minus Vc.
Yes. Okay. So here if I write this, please note this all are as a function of time. This Vct is a function of time here. So if I write now, this is Vs2 equal to IR. So what I can do is we can write I as C dVct by dt times R minus Vct equal to 0. Can we write like this or not? So here it will be C R dVct by dt plus Vct. I have just taken all the terms to the right side. ये ठीक है? Any doubts here? So I can divide by RC on both the sides. So before going there, let me tell you one more thing here. So if I write like this, if you recall in our earlier case, when I wrote the differential equation, at that time on the right side it was 0. Okay, and now it is Vs2. Now it is Vs2. So what happens is, basically this particular case where we had this thing, let me tell you this one. This is basically called as source free differential equation. It is also called as source free first order differential equation. And why it is called as source free first order differential equation? Because the right side of this term, right side here, actually it is called as a forcing function. It is called as a forcing function. Right now in this particular circuit there is no forcing function here because there is no voltage source applied here. So it is not coming on the right side. So if it is 0 here, that means the new circuit which you have formed, there will be no current sources and voltage sources which are called as the forcing function. So if you have 0 here, means there is no voltage source and the current source in the modified circuit after time t equal to 0. Okay. So because of the voltage sources and current sources, that value actually comes out here, and then we call them as first order differential equations, and the terms on the right side we call them as forcing functions. So here if you see, in this particular case you have this voltage source now. Earlier this voltage source was not there, it was a short circuit. So if this voltage source is there, then this will come on the right side. As you can see, it's naturally coming also, and there is no point in having any confusion here. So this is just the terminology, and this is basically called as forcing function, because you are forcing using the voltage source. And अगर current source होता तो then we will have a current source here. So this thing, you keep this in mind, okay? And it's a first order differential equation. So now if I divide by RC on both the sides, what I get 1 by RC VCT equal to Vs2 by RC. Okay, and then what I can do is I can actually take two terms. A as 1 by RC as we had done earlier, and then I will take B as Vs2 by RC as a new term, a new coefficient. So if I do that, then what I will get? I will get dVct by dt as AVCT equal to B. So this is the equation that we will get here. And now we will apply that same trick which we were doing earlier, that is replacing t by t prime and multiplying both the sides by the exponential e to the power at prime. The one which we had done earlier, same thing now we will do again. So it is d by dt prime vct e at prime plus which first order differential equation?
Sir, we can like integrating factor we can find and then.
Yes, you can do various ways of doing it. There is nobody stopping you out of there. This is one of the way of solving it. So I am going by this way. You can also use any other way also, but the answers will come out to be same once you solve it. Okay?
But it is this method only that you are doing. That e to the power 8t.
Yeah, there is an integrator factor. That same thing is going on here also. So this is VCT prime, and then we have EAT prime, and then we have here BEAT prime. Okay, now what we can do, we can actually write like this. Then here you have this. And now you integrate these terms from 0 to t, ddt prime, vct prime, eat prime equal to integration from 0 to t, beat prime, dt prime. So once you do this, you will get vct prime, eat prime from 0 to t, and here you have b by a, EAT prime, and again it's from 0 to t, so your answer will be here b by a, EAT prime minus b by a. So if you expand on the left side, it will be VCT EAT minus VC0 equal to b by a, EAT minus b by a. Okay, right? Any questions here? So what we can do now is, if I want to go for calculating the values, so let me write it again in a more proper way. So it is VCT is equal to VC0 e to the power minus AT plus b by a 1 minus e to the power minus AT. This is just the rearrangement of the terms. Basically what I am doing is I am actually taking this VC0 this side and dividing the left and right by e to the power AT. So once you do that, you will get this answer. It's just the manipulation of the terms. And here if you write VC as infinity, like if I want to know the capacitor voltage at infinity, so that will be what? That will be VC0 e to the power minus a infinity plus b by a 1 minus e to the power minus a infinity. So what will be the answer here if I evaluate this?
B by a.
So it will be b by a. Okay, and what is the answer here? We have already calculated VC at infinity.
VS2.
It will be VS2. So this is, we have already calculated here, right? If you see, we have already calculated VC at infinity is VS2. So this is this thing. So what you can do now is you can actually replace b by a terms in this equation, which is over here, by VS2. So if I do that, it will be VC0 e to the minus AT plus VS2 1 minus e to the power minus AT. We can do that, right? And if I want to be specific, then what is this VS2? It is nothing but it's VC infinity, right? So first of all, I will write it as this way, because somewhere or the other it is VS2 right now for this particular circuit. But if the circuit is changed, definitely this Vs2 will not be Vs2, it will be something else, because you know that this is for a specific example only, right? But if we want to generalize this expression, we know that Vs2 is nothing but Vc infinity, right? So we can, instead of writing Vs2, we will write Vc infinity here to write the general expression. Okay, so now if I readjust the terms, what I will get? I will get Vc0 minus Vc infinity to the power minus at, which is Vct. So this is the expression. So what is this expression? This expression is nothing but it is giving you the capacitor voltage at any time t as the capacitor voltage once you evaluate at time t equal to infinity, and the capacitor voltage once you evaluate at time t equal to 0 plus or equal to 0, whatever it is, and then you subtract the two values and you exponentiate it by e to the power minus at. To be specific, it will be actually this. T by tau, and tau is nothing but RC, and R will be now R Thevenin across C. So what you have to do is, for the circuit that you have, you can write the answer straight away by actually using this equation. And in this equation, what you have to do is, you have to know only three different values. The first value is Vc infinity, the second value is Vc at time 0. Once you have second value and first value evaluated, you can get these terms. And for tau, you want to calculate the time constant of that circuit, and the time constant is Rc. And note that R is nothing but it's a Thevenin across the C. So what you have to do is, in the circuits, you have to replace the C by an open circuit, and you have to calculate R Thevenin across it. And once you calculate that R Thevenin across the C, then you can replace here as Rc. So this is the general equation for first order RC circuit. Note here is no L is there, no L, only C and R. Any questions here related to this?
Sir, can you one summarize?
Yeah, so what happens is, I have this equation. This equation is a general equation for solving the circuits. And note that in this general equation, there are 3 points which are required to solve this equation. The 3 points are Vc at infinity. The second point is to calculate Vc at 0. And the third point is to calculate tau. So once you have these three values in your hand, you can actually plug in this equation, and you can get the voltage across the capacitor at any time t. So the voltage at the time c equal to infinity, you can easily calculate, right? We have seen that how you can do it for this, right? Just draw the circuit, see where it is opening and whatever it is doing. So you can calculate Vc infinity easily. Similarly, for Vc at 0 plus 0 minus or 0, it is equal to Vs1, because we have seen it from minus infinity to 0 in minus, you will draw a circuit and you will open circuit it and see what that value is. So all these things are easy, right? The third one is tau actually. Tau is Rc. So what I was telling is, in this particular case here, if I want to calculate the Thevenin resistance of this circuit across C, then what is the R Thevenin here? Across this circuit, what will that be? It will be R, because R Thevenin requires voltages to be shorted out, and across the capacitor you want to calculate the R Thevenin, so you will remove the capacitor and you will check the R Thevenin from this side, right? So once you check the R Thevenin from this side, its value is R. So that is why this R is coming here easily, right? So in this case it is R. But now let us say, if I change it by, again, if I insert R2 here and this is R1, then what will be the answer? And if I put like this, if it is not there, suppose, then what will be the answer? R1 R2 divided by R1 plus R2. So is it parallel or series or what?
It is parallel.
Parallel, right? So if you have this type of circuit, and then what will happen? Then you have to replace uh, this particular term by R1 plus R2 times C in the first case, and in the second case it will be R1 parallel R2 times C. That is what I was telling. Okay?
Sir, one doubt.
Yes.
Sir, RTH we have to found.
No, yes, so just a second. It will be, just a minute. It will be on top because tau is one. Ah, yeah, okay, it's right. Yeah, please. What is your question?
Sir, this RTH we have to find that T equals to 0 or T equals to 0 plus.
0 plus. The second circuit where it will change.
Okay, sir.
Okay. Okay. Any questions here? Okay. So if there are no questions, let me quickly solve one question and then we will close this class. And let me see if I have that or not. Okay, so let us solve one question here, and then we'll close this class today. So here we have, a voltage of 24 volts, and then we have a 3K resistor. Okay, and then we have a 100 microfarads capacitor, and we have here, a 4K, and then we have 1K this side, and we have a current source of 4.5 milliamps this side, and then we have this circuit. And now what is the thing? At time t equal to 0, the switch moves from here to this side. So we want to calculate the voltage across the capacitor here. Okay, so if I want to calculate the voltage across the capacitor VCT, so at time t is equal to 0, this switching is happening. So what will happen at time t is equal to 0? What will be the capacitor state, like from minus infinity to 0 minus? Will it be closed or open?
Open.
So it will be open circuit, right? Can anyone calculate what will be the capacitor voltage here? What will be the capacitor voltage? So we call this as actually VC0 minus. So what will be the capacitor voltage? Huh?
6 volt.
Yes, it will be 6 volts. So it's very easy. I think if you're not able to calculate, then I think some problem with you guys now, because already the course is more than half completed. So you have to practice a lot if in case you are not able to solve it. So this is 24 volts here. It's very easy, right? No current going in, so all voltage will appear here, and this current source is floating around here, so it will generate a value of 18 volts here. So this is 18 volts. So if you subtract the voltages across, you will get 24 minus 18 as 6 volts. So VC0 minus, we know already it's VC0 plus, so it's 6 volts. So VC0 plus also is 6 volts. Now what we want to know is, we want to know VC at infinity, because the equation requires us to calculate the value of VC infinity. So at VC is equal to infinity, what will happen? How the circuit will behave? Capacitor will be open or closed?
Close. Sorry, open.
It will be open, right? So at VC at infinity, the circuit looks like this, and again this will be open circuited. So if it is open circuit, can you calculate what VC infinity is? What will be the answer? Sorry? 18. It will be 18 or something else?
Minus 8.
Yes, right. It will be minus 18. So VC at infinity is minus 18 volts. So you know VCT is nothing but VC infinite plus VC 0 minus VC infinite e to the power minus t by tau. So you know it is minus 18 here, and you already calculated VC 0 as 6 volts, right? 6 volts, right? 6. Then you have minus of minus 18 t by tau. So what is the answer here? So it is minus 18 plus, you have 24 e to the power minus t by tau, and tau is nothing but RC. So what is R here? What is R? R is 5. R is 5k. So your tau is 5k times C, and if you multiply the two, you will get, I guess, what will be the value? Can anyone tell me? 2, right? Or 0.5 here. This is 0.5, right? So once you substitute this, you will get this answer for t greater than 0. But if you want to write in a single compact fashion, then it will be ut. So this is the answer for the capacitor voltage at any time t. So you can actually calculate all the values from minus infinity to plus infinity from this expression. Any questions here regarding this? How we solved it? Okay, fine. So if there are no questions, then we'll close this class today, and in the next class we will meet again. Thank you.
Sir,
Yes.
here we calculated 18 volts. So how in the V at infinity it is minus 18?
You tell me why it is minus 18. See, here it's 18 volts, right? Okay, the sign here is plus minus, so if you move around the loop, you will get minus 18.
Oh, yeah, sir. Okay.
Okay. So, any other questions? Okay, so if there are no questions, then I'm closing this class today, and then we will meet in the next class. Thank you.